Thank you. Okay, so first off, one thing I've found is not a lot of people here actually know what Zeebox is. I'm more familiar with speaking to Scala conferences where we tend to be better known. To begin with then, Zeebox, we call ourselves a companion app. The broadcasting industry calls us a second screen application. So we are a piece of software that you will run on a tablet, or you will run on a smartphone, or indeed in a web browser when you're watching television. We currently are targeting live television, so we're really going for the whole interactive angle, allow people to maybe vote on the best singer in some reality program, or to see live statistics about an ongoing sports game. And of course the broadcasters absolutely love this because it gets more people on live TV watching adverts, revenue stream, etc, etc. And let's hope the browser comes up in the right window. So I'll give a quick live demonstration of how we actually work. Okay. So this is your entry point, the home page on the application. You can come in instantly. You can see we're telling you programs that are especially popular. We give you a short list there. We give you an idea of how much something's being discussed on Twitter, the size of the audience, and that's based entirely on our own numbers, people using the application. We can, no, we're not showing any at the moment, but if somebody's mentioned a particularly noteworthy thing in a tweet, that might appear in a window here, and you can drill down into the program, and you can start to see we're showing you the Twitter stream. We can show you if any particular famous people are talking about the program. We can related applications for your iPhone, or same thing on an Android device. We'll show you applications from the Play Store. We can show you what your friends are watching, if your friends have also got Zeebox installed. So we pull in a social graph from Facebook or from Twitter to get an idea of who you are and who you know. And perhaps a bit more interestingly, we have what we call Z-tags. And these are actually produced live throughout a program. We will sit there, we will actually monitor the subtitles against a program, or closed captions as they're called in the States, and we can pick up particularly interesting topics. You can click on one of these and it will take you straight through to the Wikipedia article. And again, it will show you applications and news related to that particular topic. We also listen out for background music, so we can identify a song that you're hearing in the background of a program. You can go and download that. And in addition, we have the ability for broadcasters to add their own content. So there was a program we did quite close to our launch. It was a reality TV program, one of these scripted things, and we were actually popping up tags showing venues that people were in, and they were just scheduled to come in at a particular point of time throughout the program. We also allow customization, like this whole artwork screen up here. And finally, we have an electronic program guide, where again you can go in and you can sort it by how many people are watching, how many people are talking on Twitter. Maybe you're only interested in food and leisure programs, so we can filter that down. It makes it a lot easier to discover what's on television. So back to Keynote. So that gives an idea of what the program is, and there's a lot of bits that have to go together to make it work. We have to deal with static content, which is your program guide. We get that in from a third party. We have to do a certain amount of data cleanup, of course, because nothing is perfect. We have the custom content where people can add their own artworks, stuff around the brands, which is really quite important to us. We want engagement from the broadcasters. So the broadcasters will actually go out and say, hey, download Zeebox now. And that's where we get our customers coming in from. We have the Z tags, of course, which is completely live on demand. And perhaps most challenging is the accounts. Because we have different scalability issues for all these areas. The big data, of course, just keeps getting bigger and bigger and bigger. Most of that is stuff we're pulling in from Google Analytics, so we can try and understand what people are doing in the application. That lets us decide on new product features. We can tell where people are interested. And Scala doesn't especially solve any of these problems, which is probably not what you're expecting me to say. So the static content, well, we just use a content delivery network. Everything is hosted in the Amazon cloud, so we just push that out to the edge of the network, let it be delivered. Everything is pretty much done with JSON. So the front-end application is JavaScript or Objective-C or Java on Android. And all the communication is done by JSON. It's all RESTful web services. The custom content and the live content, again, that will go up with a number of channels, but not with a number of users, because everybody watching a program will see the same Z tags for that program. There's nothing user-specific there. The only really sensitive area is the individual user accounts. So when you log in, you will see which of your friends are online, you will see what programs they're watching, you will have the ability to start chatting with them inside the application. That is distinct to each and every user, and that is where we are really, really pushing the boundaries with Scala and with Akka. And just to give an idea of the sort of volumes we're dealing with, we can get thousands of people hit the application simultaneously and try to sign in. And that usually comes because we've had a TV ad campaign on, or because somebody has specifically mentioned the application live within a program. And the way we're dealing with that is we're using an Akka cluster, so that we can handle round robin, and because it's all on Amazon, we can quite quickly scale up, add new nodes. We have a Cassandra database underneath that, again, because it can scale quite quickly, and it's got a lot of resiliency built in there. It's a nice clustering model, plus our ops team knew it. Always helps if you know the technologies you're working with. And we are growing quickly. We are growing exponentially. We have, we definitely have volume to deal with, which is why we went with Scala, because we pinch the best bits from almost every other language going. So Java as an underlying platform for Scala, it gives us the jar file packaging, it gives us Maven for managing binary dependencies, it gives us ability to pull in anything we want from the Java ecosystem, so we can use any third-party libraries we want. And I think of all the languages that currently run on the JVM, Scala is best at speaking like a native citizen on the JVM. The interaction with Java is pretty much seamless I mean, we have the types there, so we don't have to deal with that translation. We have the same classes, same objects, etc., etc. On top of that, we add Akka, which brings in all the concurrency primitives. And Akka is often described as an actor library, which it isn't. Akka is it's a general purpose concurrency framework, I would say. So in addition to the actors, which I think have been covered pretty thoroughly already in Erlang discussions, we have futures, the idea of here's a block of code that will complete at some point in the future. And when it completes, go and do something with the result. We have what are called agents. So an agent is a bit of mutable state, but you will send a message to it just as you would an actor, and you say double yourself or convert yourself to a string, or you are literally pushing functions in, because functions, of course, in Scala are a first-class citizen. And that bit is especially helpful dealing with futures. So this is something that I think Haskell is the only other language I've seen provides this ability, that you can map and you can flat map futures. So you can build these small bits of functionality and you can compose them using a comprehension in just the same way as you would map over a collection or anything else, which cuts the boilerplate you would otherwise have trying to follow that model. Or, to put it more succinctly, wasn't the only choice either. We did consider another language that also runs very well on the JVM, that does have good interaction, and we ruled it out. Okay, joking aside, parentheses can get messy. They don't make for nice, easy, domain-specific languages, which is something we do use quite extensively. So we have our own models for dealing with particular parts of the system, and we do write a domain-specific language for solving problems and then use that from that point onwards. If you, for example, look at some of the testing frameworks available for Scala, there's Scala Test, there's Specs2, and they are both, I think, some of the best examples going of what can be achieved, which is pretty much what I said here. Type safety, very important. A lot of it was already covered by this morning's keynote, but the issue we found with dynamic languages, and we are using some Python and we are using some Clojure within Zeebox, is unit tests are code. Code needs to be maintained in a way that types do not. If I was to write a multiplication method in a strongly typed language for integers, I can guarantee that that thing will only ever be called with integers. If I was to write the same method in, for example, Clojure, I can have as many unit tests as I want, but it's still possible somebody's going to come along with some other data type I've never seen before, push it into that method and cause an unexpected failure. So you can really pin down within type systems certain invariants that it's not possible to do in a dynamically typed language. This is ultimately what drove the decision to go with Scala, because it wasn't about its technical abilities. It wasn't because there's some special feature that makes Scala more scalable, except perhaps Akka, which is pretty awesome, I must admit. It's because it allows the people to scale, it allows the developers to scale. So the role of a programming language we found is more allowing developers to communicate amongst themselves. I certainly find that I read code a lot more often than I write it, and I know everyone else in the company does that. We've now reached the stage we've got about 50 people working in development, which is not doing too badly for an alternative language. And the vast majority of those are working in Scala. And some of them, of course, Objective-C, etc., etc. And we are scaling our systems to be able to deal with more developers coming on board, to be able to make changes to the system very, very quickly, to add new features, to fix bugs. We do have competitors out there. We do need to move faster than the competition, and being able to get more developers on board, get people cooperating, get new features in faster is absolutely essential. It's the nature of business, unfortunately. So, that's weird, it's cut off the top. So this is an idea of the sort of thing we are doing, and this is, again, a domain language that we implemented, and this is for dealing with Google Analytics. So what I'm building here is a specification for a query to be run against Google. So the Google API, it uses XML, everything is strings, it's a bit hairy to deal with. We wanted a layer on top. So what I'm saying here is, first I'm creating this specification, I'm calling it sessions, and this is what we call a symbol. It's an interned string, essentially. So I start off, I take a symbol and I've enriched it with an implicit conversion. So when the compiler says symbol plus, it will say, well, plus is not a method on symbol. And it will go off and it will look for any defined implicit method that can convert a symbol to something that does have that operation available. And in this particular case, I converted to something I call ACK, which is short for accumulator, because I'm accumulating the spec here. So it will find the symbol, it will convert it, and in turn, so that builds an accumulator. I then add this thing, which returns another accumulator. So we're not mutating state here. It's fully persistent. I'm adding this, I'm adding this, I'm adding this, I'm adding this, I'm adding this. And the difference between plus and minus is just down to the way Google Analytics works. It has these concepts, what it calls dimensions and metrics. So a dimension can be absolutely anything, and you can filter on it, and you can query it, and it can contain strings, etc. A metric is purely a numeric quantity, and it is generally used for building up aggregates. So if you have a particular page, if you ask for just the page path and the number of page views, it will give you the total number of page views for each path, for example. And the more things you ask for, the more it breaks down the data and gives you fine-grained stuff. We're using pre-existing notation from Google here. So all of these things have a common super type, what I'm calling a fetch column. And fetch column is what makes this all type safe. So if I've got an accumulator, the plus method can only accept a dimension as an argument. That can only accept a metric. Filter can accept anything. So we're using subtype polymorphism. Sorry, somebody had to. And again, we're just using functions as a first-class entity. So what this will do is it will take a single field and it will break it up into multiple fields. We pass parameters in our URLs that we want to split out in our warehouse into different fields. Timestamps, for example, is passed in as a parameter that allows us to break stuff down without having it, enforced aggregation. And
so star here means
multiplication. It's not multiplication, no.
Okay.
So
what does it mean in this case?
So the star method here on, in fact, any column within the context of building specification will say, when you actually run this thing against Google and you fetch the data, as part of the fetch, in parallel, it will apply this function to this field to split it out into multiple fields.
What's the type of page URL, the type of split page URL?
The type of page URL is, ultimately, they're all fetch columns. So a fetch column will have a name as used by Google, and that's usually something like GA:(page URL). It will contain a string size, so maximum length that we can expect. It will contain the type as well. So we're using a feature known as manifests that can represent types as values to be passed around within the system. And it has a few methods like this method. So this method doesn't actually exist on the fetch column. That method is added through an implicit conversion. So in much the same way as we converted a symbol to something that has plus, at this point we're converting the page URL to something that has that method on. And all of that goes and builds up, what's spat out at the bottom is an immutable query specification. That then gets passed through the rest of the system. So this will define a database schema. So we're using an in-memory H2 database to fetch this stuff. And we have all the information we need in there to actually go and create a table in that database to hold this. It will also drive the queries that we're making against Google, and we're using the volume of data we're dealing with, and because Google will actually start sampling data if you ask too much, this actually ends up creating multiple queries, one for each day. Because if we try and ask for more than a day's data at a time, it will sample it for you, and our analytics become a lot less useful. And these, of course, are readable even by non-programmers. People need that bit explaining to them, but otherwise, anyone who's familiar with working with Google can look at this piece of code, 5 minutes of explanation, know what's going on, and they can start adding new queries to our system, and we can build all the magic behind the scenes that will handle the database, that will handle the connections to Google, that will handle the authentication, the fetching single days at a time, etc., etc., etc. We do use this technique quite extensively throughout the system. We have other DSLs in other components. So the way the Zeebox application is organised on the back end is we're running on multiple nodes in the Amazon cloud. We have a set of nodes that deal with the social interaction stuff, a set of nodes that deal with the Z-tag dynamic content. We have another node that deals with the analytics and the data warehousing, another one that serves up the artwork from the website, etc., all communicating through JSON. We also use Scala, in fact, as a scripting language. There's rather awesome projects out there that will allow you to use the build tool SBT to create scripts. So you can write a script that will specify dependencies on other Java libraries that can be resolved through Maven within a single script. And you can just run it at the command line like you would any other Python or Perl or Ruby or whatever. It's really the most multifaceted language I've been lucky enough to encounter. Is it all rainbows and unicorns? No, sadly not. It's you can hurt yourself with Scala. It's because it is really heavily multi-paradigm. We don't have this idea that you get in Python, there is only one way to do it. There is never only one way to do it within Scala. You have a multitude of styles. There's a lot of people in the community who've come from Haskell, for example, who are using Scala because they want to be writing Haskell, but the organisations they're within have mandated the JVM or whatever else. So that code is written very heavily using lots of type classes, almost not using objects at all other than containers for functions. Sorry. We have a lot of people in the community who freshly migrated from Java, and they're largely using Scala as Java but with type inference. We have a bunch of people, in fact, who've come from Ruby, and they have their own style of writing. A classic example would be method names with an underscore question mark on the end if it's returning a Boolean, or an underscore exclamation if it's doing something perhaps slightly risky, whereas more idiomatic Scala tends to frown upon using snake case or using underscores in method names. The underscore character is already massively overloaded. We really don't want to add new ways in which it can be abused. So yes, it can be a scary language. You can get yourself in a really nasty hole if you don't pay attention to what you're doing, if you mix and match styles too much. But I think the same can be said of any truly effective tool. If you're a chef, if you work in the kitchen, you will have sharp knives. You can hurt yourself with those as well. We don't start issuing chefs with plastic scissors because of this. We make sure people learn how to use the tools safely and effectively, and we get great food as a result. I think Scala's the same. It's a tool that can be used, it can be abused. If you have a disciplined team, if you know what you're doing, it can really achieve some absolutely wonderful things. And our experience is that you don't need to go out and hire Scala developers in order to do this. It's enough to have maybe one good person with a year or two experience amongst a team of, say, 10, so that when anybody does hit a point that they're wondering, well, what's the best way to solve this particular problem? There is someone there available for that person to ask, and to just make the idioms all mesh together properly, and have everybody writing a consistent style of code. And it's really taking off as a language. I know for a fact that every single international investment bank in this country has at least one team working with Scala, which certainly wasn't the case when I started using the language maybe 5 years ago. It was unknown, it was a very risky thing to be doing. Now, of course, we're seeing some very big people working working with the language. I've actually run through that talk a bit fast. Does anybody have any questions?
I noticed on one of your earlier slides you're using Node. You choose Node over, say, class.
So,
Where you'd be using Scala Akka.
so I was, can't find that slide now. So I'm not saying that we're using Node. I'm saying that these are features available that are more commonly associated with other languages. So if you go to anyone at this conference and say, what language would you use for writing actors in? You know, the answer is going to be Erlang. Node seems to have built up a reputation as being a language for the asynchronous callback type programming model. Your category theory type work is clearly the domain of Haskell. But all of these are available in one place.
Okay, I'm sorry, I didn't understand that. Okay, so can you talk a little bit about your experience using Akka and the challenges that launch programmers were perhaps more used to alternative development in Java? And do an Akka-based model?
So the biggest problem we had, we did start out working with an actor model, and we actually ended up migrating that to the more asynchronous data flow type model. We have to deal with slow external systems, Facebook probably being the worst possible example that anyone could imagine. It's a truly hideous API and a slow API. So when somebody signs in, they say, okay, I'm a new Zeebox user, I want to connect my Facebook account so you can see my friends, so I can see what they're watching and chat with them and invite people to watch programs with me. We will make a REST call, and that will return a future to be completed at some undetermined point in the future. And that future we can then map over it because it's monadic. We can also, for example, start flat mapping futures. So if we needed to call 3 external services, they will all return a future, and you can then perform a comprehension over them. So you can say for A in future A, B in future B, C in future C, return A plus B plus C. And that will itself return a future representing the sum of those 3, and that future will complete when the 3 input elements have all completed. We've also built up little bits of infrastructure so that we can, for example, linearize a list of futures. So if we have a collection of multiple futures, we can say, wait for the first one to complete, then wait for the second one to complete, then wait for the third one to complete to force a particular sequence of execution. And as a building block, they're much more easily composed than actors are. And composability has turned out to be the key to allowing us to make very, very rapid changes, to innovate quickly, and to maintain the code base.
So I was hoping you'd say something about real-world scaling, Scala Akka. And in particular, I've got a student trying to do some work with a typed version of Akka.
Okay.
So we want to do the most basic thing you do with Akka, which is you build a supervision tree so you have a reliable process.
Yes.
And so I thought, oh, right, well, we better test this. So we should use the standard testing techniques to make sure that this works.
Yeah.
We haven't found a single thing on what the standard testing technique to make sure that this works is. So what do you do about testing your supervision trees?
We don't use supervision trees very much. We tend to use the asynchronicity and the futures built into Akka. They're certainly a lot easier to unit test compared to actors.
So these are scaled down across multiple processors? Is that right?
Yeah.
So what do you do if one of the processors fails? How's that dealt with?
So you're talking, for example, if a user tries to sign in and a process fails, that future will ultimately time out. Oh, sorry. That future will, for example, time out. So futures and actors can interoperate. So you can send a message to a remote actor and await a reply as a future. So if that remote actor is on another system and that system goes down and you've specified a timeout, that future will then fail, at which point you can say, okay, we've now got a failure, we can go back and we can retry.
And on the other system, presumably, you need something to find out that it died and restart it. How do you do that?
We have a set of monitoring systems. So all of our web services, all of our components have a number of standard endpoints that we use internally for monitoring, all returning JSON. We've got one called status, and that will return information like the particular build number, when it was built, certain configuration variables. We have one called health check that will say if that system is okay, and also if any of its dependencies are okay. So if we had a component that uses Facebook and it gets an error back from Facebook, that health check will say, okay, one of my downstream requirements is no longer downstream, it's vanished, it's died, it's returning dodgy data, etc. And all of that, we have a live monitoring system that goes around and polls everything on a regular basis. We'll start sending out the usual SMSs and emails and wake up whoever's on overnight support, for example.
So to follow on, there's one thing about noticing somebody's died and giving them a kick and restarting.
Yeah.
There's another issue of either dropping messages or tweaking messages, right? Because retry maybe putting something into the mailbox, which then you can pick it for a second time and it goes back. So how do you guys handle the fact that you're highly asynchronous and you've got a number of scenarios where you can either be dropping messages or duplicating, and how do you do tests for that?
To be honest, it doesn't actually turn out to be an issue for our particular platform. If we end up logging somebody into Facebook twice, it's not a big issue. When you log somebody in, you download their friends list, you'll then go to the database and you'll say, oh, this user's already there, and it will just update that existing information. A little bit extra work will have been done, but we won't end up with any consistency issues.
So you established that all your actors are entirely stateless, so you're not having an actor pick something up?
Yeah. The only state is held in the Cassandra cluster.
And you have no transactions that people would mind duplicating?
No.
So that's a special case, I think, from what you were after.
If
Well, I was just going to ask, supervision trees are sort of about kicking things and restarting them when they
Yeah.
fall over. So why didn't you use the supervision trees? What way did they not meet your needs?
We just didn't need them. We're not in the kind of scenario where this isn't a hypercritical application. If somebody can't log in, we can show them an error message saying sorry, we couldn't log you in. It's not a trading platform. So we don't have quite the same requirements for the really, really tight stability and lack of repetition and transactional semantics that maybe other people absolutely need. I must admit, I don't work on the part of the application that deals with that social side, the whole presence information and chat and everything. So I'm not fully aware of everything that is going on in that part of the code base.
It seems as an organization you've decided to leverage DSLs as like a general problem-solving method when faced with a problem.
In a few places, yes.
Can you
when is a problem big enough to deserve a DSL?
Indeed, or organizationally, do you think in these terms, or what is that?
Once something starts to look a bit boilerplatey, you've found yourself having to repeat the same structures a few times, it starts to make sense of, okay, let's build something specific to represent this problem. One of the issues we have had is how to deal with the fact that we are hiring quite rapidly. And the ability for a new person joining the company to be productive in the shortest space of time. And we're doing quite well at this. We hired somebody last month, their background was pure C++, and they were writing production code on their first day in the office. And we've found that the DSLs really help with that. So that is where we are needing to scale. We're needing to scale the people, not the computers. So the computers are getting faster by themselves all the time, thank you very much. But a developer does not automatically get faster unless you start using the right tools and the right abstractions to let them work at a higher level. And the DSL I showed. So the DSL I showed here is readily understood by anybody who's got any experience with Google Analytics and a few minutes. Whereas there are parts of Scala that would take a bit more time for people to become familiar with. Yes?
In that expression there, is it valid to be out to user ID or
Oh yeah, this is a completely arbitrary list. We've got tens of these things defined, all containing different fields.
Right, so, but it's okay for Google if it's still a well-formed message you send to Google without those fields.
You can ask for, actually you can have a valid query with no dimensions at all, with just a single metric, for example. So if you ask for page views and you specify a date range, it will come back with a number. How many pages were viewed overall on the date?
I guess where I'm going is, do you go far enough with your DSL to make it so that it's a syntax, it's a compilation error to go on with the query compilation?
So yes, basically. This make spec method expects the accumulator type, and the only way we can create one of those is by using either a plus or a minus on a symbol. So at some point you will have had to have given it a name and specified at least one field to go into that query. Otherwise you don't have a valid thing to pass into that method, it won't compile. So the types are absolutely acting as a test for us here. And there is a balance. DSLs can be hard to write. There's certainly some of the trickier aspects of Scala code. Certainly if you look at the implementation of Scala test, for example, you will see some very, very interesting constructs necessary to make stuff read naturally. But the trade-off is that you maybe only have to write this DSL implementation once, but it pays back every single time you use it. And if it's something you're doing over and over and over again, nobody else?
I'm just wondering what makes a person to write this DSL language compared to just taking to Java and abstracting the Google query with a little button that lets me express the query in the same convenient way. It's just a little bit different. But I don't have to take care of creating all the DSL.
The actual APIs. So Google does supply a Java library for doing this, but that API is actually fairly heavy on the boilerplate, and it does rely quite heavily on mutable state, which is something we try and avoid. So we will wrap that and we will hide that from normal use.
Can it be just hidden by using an layer, but the pattern builder, using the builder pattern, in fact, to provide just a layer of things in Java?
Within Java we could certainly use a builder, but
Just discussing domain-specific languages as if it was a sort of separate thing, but in Scala, or indeed in Haskell, the domain-specific language simply is a library.
yeah.
Right? It's just a well-designed library. So it's not a new kind of thing. It's not a. So in some ways, you were saying, when do you decide to build a DSL? When do you decide to build a library? It's what we do, right? Fundamentally, we build things by building abstractions, and around some of them we think, here's a carefully enough crafted piece we can call it. It's a language of its own. But it's almost it's a difference of degree rather than kind, almost, when you get it. You start thinking it as a language. So I think there's a more gradual slope.
My experience is that most libraries ultimately end up having some form of DSL because it's just a natural fit for what they're doing. Okay. Anyway, I've been told time's up, so thank you very much, everybody.